Welcome to NPTEL Power System Protection course, Module 4 on directional relaying, lecture 16 on negative and zero sequence directional relay. In this lecture, we will explain negative sequence and zero sequence component based directional relaying principles, how they can be useful for identifying the direction of fault. By this time, we know how positive sequence component can be useful for direction of fault, what is the limitation of positive sequence component. Now, we will see how we can exploit advantage using negative sequence and zero sequence. So, see this negative sequence directional relaying first and then we will go to the zero sequence part. Let us consider the system same 3 bus system, forward fault F1 for relay RMN. So, for all unbalanced faults negative sequence component is available. So, this is the negative sequence network for such a situation, any unbalanced fault, line to ground, line to line or double line to ground fault except 3 phase fault. So, let us I 2 F is going through the fault point negative sequence component. This current will be divided into 2 paths. There is a forward fault F 1. So, through this relay a component will flow and another component will flow from the right side. So, what we see that the corresponding I 2 F flowing through the fault will be divided in terms of the impedances, corresponding impedances of the source, line and so. For this equivalent, for this sequence diagram, for this forward fault in this network, we have only negative sequence, no positive sequence, no zero sequence in this portion. For this network, you can write down V 2 m, the relay bus voltage negative sequence component V 2 m equals to the current flowing through this part. So, therefore, this part of current is I 2 m the relay current, negative sequence current through the relay. That means that I 2 m n into Z s L 2 plus I 2 m n Z L m 2, negation of that is V 2 m. So, V 2 m equals to minus I 2 m n Z S L 2 for the source, Z L m 2 for the line section. So, this is the relation. Now, if I put this I 2 m n divided by minus V 2 m m, then I got I 1 upon Z S L 2 plus Z L m 2. That leads to, if I go to the angle like the positive sequence perspective. So, angle of this equals to angle of this, where angle of this means negative angle of this impedance. The impedance, which impedance? The impedance behind the relay, negative sequence impedance behind the relay. So, we say that if we designate this angle to be phi 2 for negative sequence, angle of I 2 m n relay current, negative sequence relay current minus angle of minus of the relay current, relay voltage V 2 m, that equals to negation of the angle of the impedance behind the relay. But this impedance, if you see line impedance from the source impedance, there will be a large angle for that, more than 80 degree kind of thing. So, therefore, we say that the phi 2 will be negative for this situation and this situation is forward fault. So, phi 2 becomes negative for this forward fault. This is evident, clearly evident from this sequence network for negative sequence and based on this voltage current relationship. So, what we see from this, that this network we do not have any ZF or RF. So, these relations which we are narrated here is independent of RF. So, the conclusion that the phi 2 negative sequence angle, that angle we have defined here, angle of negative sequence current by the seen by the relay minus angle of negation of negative sequence voltage seen by the relay. This angle what the relay will see during fault, if it happens to be negative, this is a forward fault. So, that is not affected by the RF as evident from this diagram and these relations. Note that further that transmission system also the amount of unbalance during normal operating condition is also very low. Negative sequence current during normal condition is pretty small. Unlike load voltage, load current, they are the positive sequence component. So, positive sequence current in a transmission system is significantly high during normal condition also. So, that affects the positive sequence fault current that we have already observed through examples. Now, however, in case of negative sequence component, negligible negative sequence current in a line, that means that the negative sequence current here is not affected by the loading condition. So, that leads to another advantage, that this approach using phi 2 is advantageous in terms of no effect by RF and no effect by the pre-fault load condition or the load condition or the load current. That is the advantage of the negative sequence over the positive sequence component. We will see through different examples also. Now, before going to that, we will see through phasor diagrams how can you conclude the same logics. Let us say this is the system. We will consider first the forward fault as seen by the relay RMN and the corresponding phasor diagram, and then we will go to the reverse fault F2. So, let us consider this is a phase A to ground fault at F1. So, VA goes down, VB, BC they remain intact almost at the relay bus. So, VB, BC and VA. Now, we will have to compute the negative sequence component. So, VB alpha square VB 240 degree rotation, alpha VC 120 degree rotation. So, VC comes to VB position and VB goes to BC position interchange. These two will be added plus the small value of VA. So, therefore, the resultant of these three phasors what we discuss will be coming in this direction, and that is nothing but 3 V2. So, we say V2 equals to 1/3 of VA plus alpha square VB plus alpha VC. So, that means that this is 3 V2. Now, in this situation of F1 the forward fault, the current direction through the relay will be like this. The corresponding current will lag the voltage. So, to this VA the corresponding current in the positive, the corresponding current in phase A IF F1, F1 means fault F1. So, will be this one, but this will be nothing but 3 times of this negative sequence current, because for the line to ground fault IA1 equals to IA2 equals to I0. So, therefore, we say that this IA current for this F1 fault will be 3 times the negative sequence component. So, this will be the negative sequence current direction and this will be the negative sequence voltage direction. Now, if we invert intentionally to bring it to the VA reference, just like we did in case of phase component based approach, even to the 90 degree approach, quadrature approach, that is BBC, we shifted that 90 degree to bring it to the VA axis. So, therefore, if you like to bring this, you can say that 3 V2 to VA axis, then this becomes equals to minus 3 V 2. Now, if you consider the corresponding angle between I 2 and V 2, then this gives us phi 2. So, in earlier slide we saw that the angle of I 2 minus angle of minus V 2, and now also here this minus V 2 is coming and this angle of I 2. So, angle of I 2 minus angle of V 2 will be what we observe here. For the forward fall, the corresponding phi 2 is lagging, like we saw in case of VT sequence method also. So, the corresponding angle becomes negative for forward fall. Now, we will see for F 2 the reverse fall. In case of reverse fall, the current direction changes, voltage is similar in nature, same V A, V B, V C position, 3 V 2, current is reversed. So, current is upward now in phase A to ground fall this is we are considering. So, therefore, I 2 direction becomes this one. So, I 2 position of this, in a similar way minus 3 V 2 becomes this. So, minus 3 V 2 and I 2. So, we see that for F 2 fall which is reverse fall for this relay, the angle becomes phi 2 becomes positive, because I 2 is leading to minus 3 V 2, similar to we observe in case of VT sequence approach. So, the conclusion is that the phi 2 becomes positive for reverse fall. And how to get the phi 2? Angle of I 2 minus angle of minus of V 2, that is seen by the relay, that computed by the relay. I 2 computed from the set of current measurements, V 2 computed from the set of voltage measurements V A, V B, V C. So, therefore, we say that the operating quantity for this relay, negative sequence based relay, is I 2 and the polarizing quantity is minus of V 2. Let us see examples on this. Same 9 bus system, same 2 relays for 8 and 9, fault at F 1, forward fault for R 1, forward fault for R 2. Now, let us see AG fault, RF is small here in this case 1 ohm, relay R 1 and relay R 2, set of measurements current and the voltage. From the current compute the I 2, I A 1/3 of I A plus alpha square R B plus alpha I C. So, we get this corresponding I 2. Similarly, from voltages we get the V 2. Angles are important for us in computation. So, angle of I 2 is minus 147 and angle of V 2 is 84.40, but note that we require minus of V 2. Now, what does minus of V 2 implies? If this is V 2, this is minus of V 2. So, minus of V 2 means not simply putting on the magnitude part negations, it is the angle rotation by 180 degree. So, we are talking about a phasor rotation by 180 degree. So, how to do that? So, the angle part will be having a negation of 180 degree. So, this minus V 2 becomes equals to 25.8, 84.2 minus 180 degree kV, that leads to a situation of minus 95.8 degree. Then we will compute this phi 2, angle of I 2 minus 147 minus of minus. So, that becomes plus. So, therefore, minus 147.94 plus 95.8, that gives you minus 52.14 degree. Minus angle implies it is a forward fault and which is correct for R 1. We know that this current I 2 current lags the minus V 2 by certain angle, lagging current means here in this case is a forward fault. Similarly, using this R 2 data current set, we got the negative sequence current at the relay. Similarly, for the voltage set to consider that we get the negative sequence voltage. This negative sequence voltage has to be negated again like that what you did for this minus 180 degree case, and then you consider we compute the corresponding phi 2 based on this I 2 and minus of V 2 angle of that, and then we got the corresponding phi 2 to be minus 63.98 degree, and this is negative angle means forward fault. So, for R 2 also this is a forward fault which is correct. So, both relays see the fault in the forward direction. This is correctly identified by these both relays. Now, for a F2 fault which is reverse fault for R1 and but forward fault R2, set of measurements I2 and this is B2, compute the phi 2, angle of I2 minus angle of minus B2. So, we got this phi 2 to be minus 114.86 degree, less than 180 degree, acceptable. So, this is minus angle means reverse fault, for R1 this is reverse fault. So, this is correct. Now, coming to R2, the corresponding data of current, data of voltage I2 by the relay R2 and V2 by the relay R2. So, we got the corresponding phi 2 computations by like this, and phi 2 from these two angles with the negations for this V2 as mentioned. Then we got the corresponding phi 2 to be minus 63.64 degree. So, minus angle means for this is forward fault. So, this is forward fault. So, that is what we got that this case for R1 it is reverse and this case for R2 it is forward, which is correct from the as you see for the case. Now, we will go next to this with high RF. Note that from the sequence diagram we have already discussed that RF should not affect the negative sequence based relay. Let us see relay R1, relay R2, same forward fault, increased value of RF, positive sequence was affected, not properly identified in the case of positive sequence. Now, we will see the corresponding set of measurements, current and voltage, negative sequence computation, negative sequence voltage computation. Similarly, for the relay R2 also I2 and V2. Now, phi 2 equals to angle of I2 minus angle of minus V2. So, we see from these two angles phi 2 equals to minus 52.15 degree, negative angle, forward fault, correct. This was incorrectly identified by the positive sequence approach. Now, it is correctly identified the negative, because we mentioned that RF does not affect the negative sequence component, which is true. Looking at the R2, the corresponding phi 2 is minus 63.98 degree. So, minus angle, forward fault. So, this also correctly identify the fault. So, these two relays see the fault in forward even though the RF is 120 ohm. So, this forward fault by both the relays, which is correct. If you compare the relay performance, negative sequence relay performance as compared to the positive sequence one, negative sequence has advantage over positive sequence in terms of higher value of RF. Now, I will go to the zero sequence directional link. This is similar to negative sequence. We know the corresponding zero sequence network for this system, forward fault, similar to negative sequence what we discuss, only replace the corresponding impedances in terms of zero sequence component. So, this I 0 f passing through this, and then if you write the corresponding equation from this side, same you can say that I 0 m n is flowing from this side. So, therefore, two impedances are there behind this relay. So, that is what you can write the expressions for the zero sequence voltage at this bus minus I 0 m n Z s L 0 plus Z L m 0, these two impedances, and then the angle of I 0 m n minus angle of minus V 0 m, that equals to minus of the angle of this. So, this being positive. So, the negative sign implies negative angle. So, phi 0 becomes negative in case of forward fault. Same conclusion, similar what we got for the negative sequence component current, only we are replacing the corresponding current with the zero sequence component computed from I A B I C, I A plus I B plus I C by 3, and the corresponding voltage V 0 equals to V A plus V B plus V C by 3. So, then we found that the phi 0 is negative for forward fault, and in case of the reverse fault current will be reversed. So, we will conclude that for that case the corresponding phi 0 will be positive. So, here also we see that from the diagram independent of RF, no effect of RF, and in most of the transmission system also we see that during normal operations the I 0 component is negligible. So, this is also we say that pre fault current has no effect on the zero sequence approach also. Now, going to this same phasor diagram perspective similar to that one, let us consider for the F1 fault, for the line to ground fault we will have this similar diagram. So, VB, VC and this VA. Now, we will compute the V0, V0 is VA plus VB plus VC. So, you add VB, VC and add VA. So, this again comes out to be this line 3 V0. If you like to shift it to the VA line, then minus 3 V0. For F1 fault, IA lags voltage substantially in terms of the impedance angle of the line and the RF. Now, in this you can say that current is 3 times of the I 0 F, IA equals to 3 times of IA 1 equals to 3 times of IA 2 plus equals to 3 times of the IA 0. So, that leads to that this IA 0 is this line and minus 3 V 0 is this. So, minus V 0 and I 0. So, therefore, if we define this as phi 0 as already mentioned in the earlier slide, like the negative sequence component, these slides, this current is lagging to this voltage, reference voltage, polarizing voltage. Therefore, the phi 0 will be negative in terms of that, and phi 0 negative means the corresponding fault is forward fault. Similarly, for F2 the current will be reversed, and this current is also the direction of the I 0. I 0 similar to this voltage minus 3 V 0. So, to this reference one the corresponding current leads, and angle of I 0 minus angle of minus V 0, that becomes positive. So, phi 0 is positive means the fault is in the reverse direction. So, that leads to situation that we can conclude using the zero sequence component defining like this: angle of I 0 seen by the relay minus angle of minus V 0 seen by the relay bus at the relay, then the corresponding angle, if it comes out to be negative, it refers to forward fault. If it angle comes out to be positive, it says this is a reverse fault. So, therefore, the corresponding zero sequence based approach also, zero sequence current seen by the relay, angle of the polarizing quantity becomes minus of V 0 in this case. So, that gives us, you can say that the principle of zero sequence based approach. Of course, similar to other things from the phasors, we can conclude that this angle phi 0 is limited to plus minus 180 degree. Looking at this performance of zero sequence 1. So, the first case with forward fault F1 for R1 and R2 in this 9 bus system, set of currents, set of voltages. So, I 0 computed, this is the angle minus 146, B 0 this is the angle. So, we have to negate this B 0. So, that means that minus 180 degree to this angle, and then similar to the negative sequence component what you did, if you compute this phi 0 with the angle I 0 minus angle minus V 0, for this case the phi 0 happens to be minus 45.79 degree. So, this negative angle clearly says this is a forward fault, R1 this is a forward fault. So, this is correct. For R2 this is also forward fault, set of measurements of current and voltages, computed this I 0 and V 0, negate the V 0 with minus 180 degree here. For this case, compute the angle I 0 and the angle of minus V 0, and then this subtraction got the phi 0 to be minus 66.15 degree, negative angle implies forward fault, R 2 sees it forward, which is correct. So, both relays sees the fault in the forward direction. Case 2 for F2 fault forward for R2 and reverse for R1. For R1 set of measurements, for R2 set of measurements, phi 0 computation using the relation, phi 0 for R1 happens to be positive 150.44 less than 180 degree. So, this is a reverse fault clearly, and for R2 the phi 0 computed is minus 66.98 clearly a forward fault. So, that leads to, you can say that conclusion that R1 sees it is a reverse and R2 sees it is a forward, which is correct. So, the judgment by the two relays using the 0 sequence component is correct. With high fault resistance, already mentioned like native sequence component, this sequence component approach, 0 sequence component approach is not affected. So, we will see, you can say that in this case what happens to this situation. R1, the corresponding I 0 is having an angle of minus 115.81, V 0 is having 109.99 degree, phi 0 computed by these relations comes out to be minus 45.80 degree, minus angle forward fault. So, for this forward fault, so RF has no effect, that is true now. R2, for R2 the corresponding phi 0 comes out to be minus 66.15 degree, same you can say that. So, the corresponding forward fault, that leads to consider forward fault case. So, forward fault for both relays which is correct. So, the we see that this is compared to positive sequence, this has advantage and is similar to the native sequence perspective. Now, in general remarks, the native sequence and 0 sequence directionally laying both have advantages over positive sequence, because they are not affected by RF and also not affected by the pre-fault conditions, because systems generally operate in close to balance condition. So, no negative sequence or 0 sequence component normal time. Therefore, such an approach is also more sensitive, because the effect of pre-fault is negligible. For balance fault, however, there is no 0 sequence or negative sequence component. So, they do not have any answer to the direction of fault in case of 3 phase fault. It means such an approach cannot provide solutions for all situations. It means that we have to switch over to, if we are using the sequence component approach, we have to use the positive sequence approach. So, that means that the sequence component they can complement each other. 0 sequence has problem with mutual coupling, particularly on parallel transmission system, and so we know 0 sequence is a single phase perspective. So, therefore, flux becomes additive. So, it has 0 sequence mutual component issue, and that means that if you have such a, if you are going to apply for such lines, then it may be disadvantageous. In that case, native sequence can have advantage. Negative sequence and positive sequence, they are not affected by the mutual component perspective, and so. So, we say from these two diagrams that clearly sequence diagrams for the positive and negative, that they are not affected by the RF, that is the beauty of, you consider the two sequence component, 0 sequence and negative sequence component. Now, we throughout these discussions for positive and negative sequence and the 0 sequence relays, we discuss about only line to ground fault, AG type fault. Now, going beyond that, for all other categories of fault, line to line, double line to ground and 3 phase fault, BC, BCG and ABC, we have set of measurements for fault at F1 and fault at F2, reverse fault for the corresponding relay R1. So, forward fault and reverse fault. So, we have set of measurements for line to line fault, double line to ground fault and ABC fault. So, these are the sets of currents and voltages for this case, for the both forward and reverse fault case for relay R1. Now, for forward fault F1, first case for the relay R1, if you see BC, BCG and this, then this sequence based, you can say directional link positive sequence, I1 computed, V1 computed, angle phi 1 is minus 66.13. So, this identifies as forward, which is true. Native sequence, 0 sequence, native sequence component becomes I2 and minus V2, and then the corresponding angle is minus 52.15 degree. So, this is correctly obtain directional relaying. For BC fault there is no zero sequence, they do not have any you can say that answer to this. So, they cannot decide on this. For BCG fault positive, negative and 0. So, this set of you can say that things are there. So, then we have you can say that this, and then all the three you can say that are correctly identified, because negative signs indicate forward fault, forward fault. Now, in case of the ABC fault positive, negative and 0. So, ABC fault means only positive is available, 0 negative sequence and 0 sequence they cannot respond to consider to this such a situation. So, positive sequence case the angle comes out to be minus 83.08 degree, and this large angle is because of the no RF value, angle of this transmission system and so transmission impedance. So, this is forward fault. So, that means that for all the other types of fault in the forward directions, the corresponding relays principle perform as expected. Going to the reverse fault, for this F2 fault for this R1, the set of relay you can say that we see you can say that for all the cases the corresponding angles are positive, and therefore, the corresponding reverse fault is being identified properly by the different sequence component. However, as usual for the line to line fault and for the 3 phase fault, the zero sequence component is not available, and the negative sequence is not available for the 3 phase fault case. So, in general from the set of observations for different types of fault besides line to ground fault, we see that they are good in identifying the direction of the faults. So, in overall we can have some remarks on the different aspects of performance aspects of the positive, negative and zero sequence relaying principle. Positive sequence is available for all faults, they can conclude for all faults, but they are affected by RF, more RF, poor performance. Effect of pre fault, if the pre fault is dominating close to the fault component of current kind of thing values, then the relay decision may be affected. No effect on mutual coupling, negative sequence available only for unbalanced fault, not affected by RF, not affected by the pre fault, because pre fault does not have a negative sequence component, no mutual effect. So, this is the strength. Zero sequence is only available for ground faults, no effect for RF, no effect for the pre fault condition, but it is affected by the mutual coupling, particularly applications to parallel transmission line also. So, we see that there are different sequence components which can be applied for identifying the direction of fault. They are very good at, and they can complement each other for a better performing relaying principle. Thank you.